Hi, I'm Charmaine, and I'm a second-year graduate student at Harvard University. Today I want to talk about the pigeonhole principle, which is a very useful principle in solving mathematical problems. It goes as follows. If we have n pigeons, and m pigeonholes for them to lie in, and the number of pigeons and number of pigeonholes satisfies a certain relation where n is greater than q times m, where q is an integer. Then some pigeonhole must have at least q plus 1 pigeons. Why do I say that this is evident? Well, if every pigeonhole has at most q pigeons, and we have m pigeonholes, then we have to have at most qm pigeons, but we've already said that the number of pigeons is greater than qm. So let's take a look at why such an evident observation is useful in solving mathematical problems. Here's an example problem. Say we have 5 points on the sphere. I claim that we can always cut the sphere in such a way we can cut the sphere into 2 hemispheres. Such that at least one of the hemispheres has at least 4 points on it. And just to be clear, we'll say that points that are along the cut will count as belonging to both hemispheres. So let's take an initial stab at solving this problem. Say I have a sphere, and I make a random cut into 2 equal hemispheres. So suppose my cut is along the equator. Then, by the pigeonhole principle, if I take my pigeons to be the 5 points, and my pigeonholes to be the 2 hemispheres, then we know that 5 is greater than 2 times 2. So this implies that one hemisphere has at least 3 points. Okay, can we improve this so as to get 4 points in one hemisphere? Well, one idea is, since points along the cut belong to both hemispheres, why don't we try to cut it such that we have at least one point along the cut? Well, let's see what happens now. We have 4 remaining points. We have 4 remaining points, so the best that we can conclude is that there would be at least 2 points on one of the hemispheres. Well, that only gives us a total of 3 points still, so that's not very good. Maybe we can carry this idea a bit further. Is it possible to guarantee that we can make a cut which would have at least 2 points in it? And well, it turns out that this is possible. This is because we need 2 points to determine a great circle in the sphere. That is, a circle in the sphere with maximal radius. So this is indeed possible. And now we have 3 remaining points. Remember, these are our pigeons. And once again, we have 2 pigeonholes, the 2 hemispheres. So we conclude that there's one hemisphere with at least 2 points, not counting the other 2 points that are along the cut. Hence we conclude this hemisphere has 2 points, not on the cut, 2 points on the cut, that gives 4 points altogether as desired. Okay. Talk about the second problem involving the pigeonhole principle. I really like this problem because it showed me just how powerful the pigeonhole principle can be. Before starting on the problem, we'll need some terminology involving sequences. So, given a sequence of integers, which we'll call A1, A2, A3, all the way until the nth term AN, a contiguous subsequence is a subsequence of the form AI. So I start from the ith term in the sequence, and then I take the term immediately following that in the sequence, the term immediately following the previous one I took, all the way until some term AK, which doesn't have to be the same as the final term of the sequence. And the key point here is that I mustn't skip over any term in the sequence when taking the subsequence. So let me now introduce the second problem. Given a sequence we want to show that there always exists a contiguous subsequence such that the sum of the terms in it is divisible by n. Let's look at an example to see how this works. I'm going to take n to be equal to 5. And I could try to create a sequence as follows. Say 2, 4, 3. There isn't any contiguous subsequence in here that's whose sum of terms is divisible by 5. Let's see. 4. I think this still works. And what happens if we put a 1 now? Well, 4 plus 1 would be equal to 4 plus 1 would be equal to 5, so that doesn't work. If we put a 2, then 2 plus 4 plus 3 plus 4 plus 2 is 15, so that doesn't work. If we put a 3, 3 plus 4 plus 3 is 10, so that doesn't work. If we put a 4, well, 4 plus 3 plus 4 plus 4 is 15, so that doesn't work either. And 5 on its own wouldn't work because we could take our contiguous sequence to subsequence to be just the number 5, so that doesn't work either. So let's now prove that indeed there will always exist a contiguous subsequence such that the sum of the terms in it is divisible by n, not only for n equals to 5, but for any n in general. You might want to pause the video at this time to try to solve the problem for yourself before looking at the proof. So, we'll consider a special kind of contiguous subsequence, not all possible ones. Namely, we'll consider those of the form which a1 sum and so on. So they have to start with the first term in the sequence. And it might be possible that none of these work. So for instance, I could have a1 plus a2, a1 plus a2 plus a3, a1 plus a2 all the way until an. So there are n such sums that I want to consider. And now we'll want to consider the remainder when we divide each of these sums by n. There are also n possible remainders. Namely 0, 1, and so on, all the way until n minus 1. If one of the remainders is 0, we're happy because we found our contiguous subsequence whose sum of terms is divisible by n. So what happens if none of them is 0? say I have two such subsequences, A1 plus all the way to AK, and say a longer one, so it's A1 all the way to AK, and then to some AL, where L is bigger than K. If these two have the same remainder, when I divide by n, then we can conclude that n divides the difference of the two, which is also a contiguous subsequence. It's the sum of the numbers from the one from the k plus first term all the way until the lth term. So can we guarantee that we can always find two such subsequences, contiguous subsequences, starting from the first term, and such that the sum of the terms in it have the same remainder when divided by n? Well, let's go back and look at this. We want two things to have the same remainder, so it sounds as though this might be the pigeonholes. And remember, if one of the remainders is 0, we're good. So now we're actually assuming none of them is 0. And now we have n minus 1 possible remainders, 1 to n minus 1. These will be the pigeonholes. And we have our sums, whose remainder when divided by n is going to go into one of those pigeonholes. So we should think of these as the pigeons. So now we have n pigeons and n minus 1 pigeonholes. So in fact we can conclude that two pigeons go into one pigeonhole. Namely, there are two such contiguous subsequences that have the same remainder when divided by n. So that's it, we're done. We take these two subsequences, take their difference, which will have to form AK plus 1 all the way until AK, and that gives us the contiguous subsequence we want. Hope you have had fun.